All right, morning everybody. Welcome back. Happy Thursday. Got a warm-up problem for you to start thinking about, related to the problem we ended on last time. If I give you the numbers 1 up through 10, and you want a subset where no element is divisible by any other element, what's the best you can do? So go ahead and think about that for a second. While you're thinking about it, I'll recap where I'm going to claim we got to last time, maybe jumping ahead a little bit. So, one of the big ideas to come out of our discussion last time was if you take all the prime numbers less than or equal to 2n, then you get a set like this that works. So, I took some examples so far and looked at that. So, if n is 1, then 2n is 2. All the prime numbers less than or equal to 2 is the set 2 that has one element. And then I have this last column, is that the best we can do? And certainly, if our set is 1 and 2, then only having one element is the best we can do. There's no way to have both elements. So then we ratchet up a step. We make 2n equal to 4. And again, we look at our primes, 2 and 3. That has two elements. Then we can again ask, is 2 elements the best we can do? And it is. So we can have 2 and 3. We can't have 3 elements. If we have 3 elements, then we can't have both 2 and 4, because 2 divides 4, which means we have 1 and 3, but 1 divides 3. So you can only have 1 out of 2 and 4. You can only have 1 out of 1 and 3. Therefore, 2 is the best you can do. And then I've extended things out a little bit. For 6, your prime elements are 2, 3, 5. For 8, your odd elements are 2, 3, 5, 7. That gives you 3 and 4 elements. We don't know necessarily if that's the best. We don't have a nice clean argument that shows that they're the best, but they're relatively good sets. And so that brings us to 10. So hopefully I've given you enough time to think through this. So what is a first guess at a largest subset of 10 with no elements that divide one another? What's a good thing to start? Look at first. Or maybe another way of thinking about it, what's the set we should start with to try and beat? Yeah, good. Our first idea should be keep doing the same strategy of taking the prime numbers less than or equal to 10. 2, 3, 5, 7. Okay? 2, 3, 5, 7 works for sure. Nothing in here divides anything else in here. Why is 2, 3, 5, 7 kind of underwhelming? 2 good reasons why it's not very exciting that I can think of, maybe more. But what might push us to maybe want to try and do better? It's the same as 8. That's one good reason. We've got more elements. We're going all the way up to 10 instead of just 8, but we haven't added anything. So that's one good reason why maybe it's not the most exciting. There's another thing here that I notice. What pattern can you see between 2n and a. Yeah, size of A, if you double the size of A, it looks like you're getting to n. Or maybe a conjecture. So we've talked about theorems a lot, but a conjecture is a theorem you haven't proved yet. So looking at what we have so far, a conjecture maybe the biggest A can be is n, right? So 2n is how many elements we have. Maybe the best we can do is n. Right? That would match up with everything we've done so far. So 2 elements we can get 1, 4 elements we can get 2, 6 elements we can get 3, 8 elements we can get 4. So that's another thing that's sort of underwhelming about 2, 3, 5, 7. That would break the pattern. We want to write 10 elements we can get 5, but this would only be 4 elements. So this conjecture gives us something to aim for. Anybody see a subset of elements of size 5 where nothing divides anything else? So let's think through this logically. Rather than just trying some stuff, let's think about what might or might not be in there. So, can 1 be an element of A if the size of A is equal to 5? Can we put 1 in our set where no elements divide any other elements? No, right? Because 1 divides everything. So if we have 1, then we're done. 1 is the only element, and we're out of luck. Okay. So 1 can't belong. Can we have 2? Can 2 be an element of A if the size of A is equal to 5? Well, okay, this is a little bit harder, but let's think about it logically. Let me write out my numbers 1 through 10. I already know I can't have 1. If I accept 2, what do I have to reject? All the evens, right? Once 2 is in, that means 4 is out, 6 is out, 8 is out, 10 is out. Okay? So if I want to have 2 in my set, and I want to have size 5, I can't have 1, already discussed that. I can't have 4, 6, 8, or 10. The only things left to have a set of size 5 is everything left over, 3, 5, 7, 9. But can my set be 2, 3, 5, 7, 9? Is that a valid set? No, right? That doesn't work because 3 and 9 can't belong together. So can 2 be in my set if I'm going to have size of A equals 5? No, it doesn't work. Okay. Now let's look at 3. Can 3 be in my set if the size of A is equal to 5? Let's do the same thing. 1 up through 10. I know I can't have 1 and 2. I've already covered those cases. I want to have 3. What does that rule out for me? Once I've taken 3, what am I ruling out? Can't have 6 and 9. Good. No 6, no 9. Okay. And so now, this time, 4, 5, 7, 8, 10, there's still 5 options. Which means I only need to get 4 of them. But can you find 2 pairs of numbers that I can't have both of? Four and 8 and 5 and 10. Good. So I can only have one of these, and I can only have one of these. So if I have 3, sure, go ahead, throw in 7. Not worried about that. You can have 7. But then you only get 1 out of 4 and 8, and you only get 1 out of 5 and 10. So if 3 is in my set A, the best you can possibly do is 4. Can't make it all the way up to 5. All right, it's not looking so good for our conjecture. But let's keep going. Next question would be, can 4 be an element of A? If the size of A is equal to 5. So I'm going to stop writing 1, 2, 3 because I already know I can't have 1, 2, 3. 4, 5, 6, 7, 9. There we go. 4, 5, 6, 7, and 9. And this works. All right, so this steady methodical approach beat our guess of 4. And now we have another one. We have another set of size 5. 5, 6, 7, 8, 9. Are there any others? So I should say yes to this. Any other sets of size 5? We found 2. 6, 7, 8, 9, 10. 6, 7, 8, 9, 10 also works. Okay. So, looking a little bit better for our conjecture now. Right? 4 is not the best we can do. We can do 5. 7, 8, 9, 10, 11 doesn't work because we stop at 10. Otherwise, 7, 8, 9, 10, 11 would be great. But our biggest number is 10, so we do have to stop there. And in the interest of time, I'm going to make another observation. Just like all the primes work, I claim there's something special about this 6, 7, 8, 9, 10. What's the general version of 6, 7, 8, 9, 10? So 6, 7, 8, 9, 10 is 1 up through 10. What's the general version in 1 up through 2n? Two n minus 1, all the way up to 2n minus 4. Claim we can do better than that even. you can think of 6 as 2n minus 4. You can also think of 6 as n plus 1. Consider the set n plus 1, n plus 2, n plus 3, all the way up to 2n. All right, so that's what we're doing here. N was 5, so I'm doing 6, 7, 8, 9, 10. Does anything in this set divide anything else? Well, if one number divides another number, what's the smallest thing it can be a multiple of? What's the smallest number you can multiply something else by to get something new? 2. Right? Can't multiply by anything smaller than 2. If you multiply by 1, you just get yourself back. And since 1's not in this set, I don't have to worry about that. So, is there any number I can in this set that I can double and stay inside the set? N plus 1. What happens if I double n plus 1? Right? N plus 1 is my smallest element, and if I double that one, I'm already too big. The smallest thing I could double pushes me outside of the set. Which means if I take anything in this set and multiply it by anything bigger than 1, I'm too big. I'm already outside of the set. So let me write that down. Multiplying anything in this set by 2 or more gives you a number that's bigger than 2n. Results in a number bigger than 2n. This means none of these numbers can divide each other. Right? Remember, what does it mean for A to divide B? A divides B means B is equal to A times some K. So what could K possibly be? Well, it has to be smaller than 2, but then it has to be 1. Which means nothing in this set, from n plus 1 all the way up to 2n, divides anything else. So I'm going to fill that in here. I'll do a new color to indicate that it's new information. 6, 7, 8, 9, 10 gets us up to 5. Okay. So let's look at our conjecture again. Maybe the biggest our set can be is n elements. Before, we were just following a pattern, but now we actually have, if you give me any n, in the set 1 all the way up to 2n, I can find a set of n elements that has this property. None of them divide another one. So in some sense, the answer to the question, what's the biggest set possible, the smallest that answer could be is n, because I can always find a set of n elements that works. Now, though, we have to ask carefully, is this really the best we can do? Is there any way to get n plus 1 elements? Can we find a bigger A? right? At first, we thought maybe 4 was the best we could do for 10. And then we did this very careful analysis, and we figured out 4 wasn't the best. We can actually go up to 5. So how sure are we that 5 is the best? Maybe we can show 5 is the best for 10, but how can we show that n is the best for 2n? And this is where we come back to the pigeonhole principle. We need to come up with a clever pigeonhole principle solution to show that n is actually the best, that our conjecture is a theorem, that this is the right answer. Here's how this works. You need to come up with, well, okay, let me actually, rather than say the answer, want to show that it is not possible that size of A is equal to n plus 1. And here's my hint. I want to use the pigeonhole principle. By the way, I think sometimes this gets abbreviated PHP. I don't know if we're going to do that on tests or quizzes, but just in case, I wanted to mention it. Pigeonhole principle, PHP. What are either our pigeons or our holes? Who can get us started on the pigeonhole principle? So just as a reminder, pigeonhole principle says if you have n plus 1 pigeons and n holes, then some holes got to have 2 pigeons. Yeah, right? So n plus 1 should set off some alarm bells. Somehow the elements of A are going to be our pigeons. Since size of A equals n plus 1, these are our pigeons. So now I need to find n holes. Where if there's 2 elements in one hole, that's a problem. Then A is not a valid set. Okay. So, what property do I want my holes to have? What makes A not a valid set? What should all the numbers in my holes, what property should all the numbers in my holes have? We actually saw this idea a little bit already. We look back at what we did. In this example, we said we could only have 5 or 10. We could only have 4 or 8. This suggests a possibility for our holes. We're going to make our holes pairs of numbers, where I'm only allowed to have 1 out of the 2 numbers. So here are my holes. 1 and 2, 2 and 4, 3 and 6, 4 and 8, all the way up to n and 2n. Out of these n holes, I can only ever choose one of the elements to be in my set. I know there's n of them because they go from 1 up to n. And I can't have two elements from one hole. Right? I can't ever have 4 and 8 both be in my set. At best, I have to go through these and pick one of my numbers from each one. So, if I have n plus 1 values, they have to fall into these n holes. Some hole has more than one value. So, by pigeonhole principle, n plus 1 values into n holes. One hole has at least two. One hole has at least two values. But then A is not a valid set. So if I have n plus 1 elements, I've listed out all of the elements of 1 up through 2n. So it's got to, or at least all the elements from 1 up to n, they've all got to fall into one of these holes. There's no way for me to avoid doubling up, in which case I didn't have a valid set. So there's no way to squeeze n plus 1 elements in. So that makes our conjecture a theorem. Theorem. The largest subset of 1, 2, all the way up to 2n, where no two elements divide one another, as size n. We know it has size at least n because we can pick n plus 1, n plus 2, all the way up to 2n. That's always an example that works. And the pigeonhole principle says you can never beat n. If you have n plus 1 elements, that's too many. You're going to have some pair that divides one another. So I've spent a lot of time on this example. I could have just written this as a theorem and written the proof and said, okay, pigeonhole principle, we use it like this, blah, blah, blah. But I wanted to really go through this to give you a feel for how math problems are really solved. Now, obviously, we didn't just solve a new problem. The answer to this question was known beforehand. But this is how real math problems are solved. You come up with a problem, and you come up with a first pass at it. Right? Our first guess was, oh, look at the primes. And you do some small examples, and you maybe see some patterns, and then you wonder, is this pattern the right answer? And maybe you make a conjecture. And you can work at this conjecture from two sides. You can work on it from the lower bound side, which in this case means creating bigger and bigger sets that work. And you can work on it from the upper bound side, arguments that your set can't possibly be too big, right? The first thing we said was that our set can't be bigger than 2n because that's everything. But then we said, oh, actually 2n minus 1 works as a bound as well, because you can't have 1 and anything else. So 2n minus 1 is an even better bound. And you can keep whittling down from the upper end and from the lower end, working towards your conjecture. And that's how we end up doing a lot of math problems. Okay. Questions there? Gonna move on then. I have one more pigeonhole principle example, then we'll shift gears. Another problem like this, pigeonhole principle does not jump out immediately as something useful. Suppose I have n squared plus 1 numbers. Doesn't have to be 1 up through n squared plus 1. It's just a sequence of any n squared plus 1 numbers. Let's say different numbers. Different real numbers. So if, for example, if n is equal to 2, then I need 5 numbers. I might pick 7, -3, pi, 10 to the 10, and, I don't know, 0. Okay, so just 5 real numbers in a row. I claim I can always find a subsequence with n plus 1 numbers in it that is either decreasing or increasing. It's either increasing the whole time or decreasing the whole time. So in my example, n plus 1 equals 3, I should be able to find 3 numbers that are all increasing or 3 numbers that are all decreasing. And in this case, I actually have both. I can start at -3, and then I can increase from -3 to pi. So this goes up. And then I can increase from pi to 10 to the 10. Or I could start at 7, decrease from 7 down to pi, and then decrease from pi down to 0. So I have an increasing subsequence, -3, pi, 10. And I have a decreasing subsequence, 7, pi, 0. I'm not claiming you always get both. I'm just always claiming you get one or the other. And I can prove this using the pigeonhole principle. And it's a really nice proof. So here's how this proof works. I I'm going to number the elements of my sequence from x1 up to x sub n squared plus 1. So I guess I've been using this color green. X1, x2, all the way up to xn squared plus 1 be a sequence of distinct real numbers. Okay. And then I'm gonna, for each value, I'm gonna come up with 2 more values. So let a sub I be the length of the longest increasing subsequence starting at position I. So let me come back to our example here and show you my a sub i's. Here is my example: 7 minus 3 pi 10 to the 10 and 0. So a sub 1 is the longest increasing sequence. It's got to increase the whole way, and it's got to start at 7. So I start at 7, I can only go up once. You have increasing, does not mean you have decreasing as well. No. So in this subsequence, I'm only increasing. So I start at 7, and by increasing, decreasing, I mean reading from left to right. So as your index goes up, the value goes up. So I start at 7, and then I want my sequence to increase. The only thing I can do is go from 7 up to 10 to the 10. All of these other options are smaller than 10. So a sub 1 equals 2. The best I can do if I start at 7 and I want to increase every time is 2 elements. A sub 2 is negative 3. We talked about how here I can have a subsequence of length 3. Minus 3 pi 10 to the 10. So I can have a sequence of length 3. A sub 3, if I start at pi and I want to go up, best I can do is 2. I can go from pi to 10 to the 10. A sub 4, if I start at 10 to the 10, I can only do 1. And a sub 5, if I start at 0, well, I'm at the end, so best I can do is 1. So those are my a sub i's. I also want b sub i's. Let b sub I be the length of the longest decreasing subsequence starting at position I. So come back to our example, b sub 1. If I start at 7, how far down can I go? Well, don't go from 7 to minus 3. That's a trap. Then you're done. You actually want to go 7, and then pi, and then 0. Have a decreasing sequence of length 3. Sure, I'll come back to A1 in a second. B2, if I start at minus 3, there's nowhere to go down. So the best I can do if I start at B2 is just to have minus 3, and that's it. B3, if I start at pi, I can go down to 0. B4, if I start at 10 to the 10, I can go down to 0. And B5, I only have one number left, so 1 is the best I can do. So let me come back to A1. I want an increasing sequence that starts at 7. So I start at 7, and I have to go up. Can't go up to -3 because it's too small. Can't go up to pi because it's too small. Can't go up to 0 because it's too small. My only option is to go up from 7 to 10 to the 10. And then once I get to 10 to the 10, I'm done. That's the biggest number. So the subsequence here that corresponds is the subsequence 7, 10 to the 10. That is the longest subsequence where the numbers only go up. Here I've got the subsequence -3, pi, 10. There everything goes up. A sub 3, I have pi, 10 to the 10, 10 to the 10 all by itself, and 0. So just as a quick check, make sure everybody's understanding, what value do a sub n squared plus 1 and b sub n squared plus 1 always have? A sub n squared plus 1 is always equal to b sub n squared plus 1 is always equal to what? It's always equal to 1. N squared plus 1 is the last number in my list. So if I'm starting at the last number in my list, the best I can hope for is 1. I'm only ever going to get 1. So here's the pigeonhole principle argument, and it's really clever, so I like showing it off. Consider the n squared ordered pairs a sub 1, b sub 1, a sub 1, b sub 2, oops, this is not a dot, 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 just a comma, all the way up to a sub 1, b sub n, and then also a sub 2, b sub 1, a sub 2, b sub 2, all the way up to a sub 2, b sub n, and then all the way down. A sub n, sorry, hold on. This is not what I want to do. Thinking of a different problem. Cancel that whole part. Okay. Try this again. I still want to think of my ordered pairs a sub I, b sub I. So think of ordered pairs a sub I, b sub I. Oops, I'm off the bottom of the page. Okay. If any of my values are at least n plus 1, then I'm done. So if any a sub I is greater than or equal to n plus 1, or b sub I is greater than or equal to n plus 1, then I'm done. Then I found an increasing or decreasing subsequence with at least n plus 1 elements. So the theorem is good. Right? The theorem said I could always find n plus 1 that increase or n plus 1 that decrease. So I'm done. Otherwise, all of the a sub i's and b sub i's are at most n. A sub I is at most n, B sub I is at most n, and this is true for all I. Now, how many ordered pairs do I have? A sub I, B sub I. How many of these ordered pairs can I create? Remember, my sequence has n squared plus 1 elements. How many different values can my index take? All right, lost people a little bit. N squared plus 1 times n squared plus 1. If I was allowed to have different indices, then you'd be right. If this was a sub I, b sub j, which is what I was thinking about up here, but is a different problem, then I would agree with you. But I'm insisting that I use the same value for both. So I'm looking at, in my example, I'm looking at a sub 1, b sub 1, which is the ordered pair 2, 3, and a sub 2, b sub 2, which is the ordered pair 3, 1, and a sub 3, b sub 3, which is the ordered pair 2, 2. Yeah, right? So I have n squared plus 1 different ordered pairs. One for each of my elements. So let me just finish this up, and then I've got 1, 2, and 1, 1. N squared plus 1 different ordered pairs. If a sub I is less than or equal to n, and b sub I is less than or equal to n, and they're both at least 1, because I can always take a 1 element subsequence, just the element all by itself, how many different ordered pairs are possible? How many different combinations can I make between these two? How many options for a sub I? Yeah, right? N squared. I've got n options for a sub I. I've got n options for b sub I. N squared total different options. Here's where my pigeonhole principle comes in. By the pigeonhole principle, I have n squared ordered pairs, n squared plus 1 ordered pairs, n squared different options. Some ordered pair must repeat. Here's where I've used the pigeonhole principle. So what does that mean? I've got my sequence, x sub 1, x sub 2. Somewhere in the middle I have x sub I. Somewhere else I have x sub j. And then I end on x sub n squared plus 1. And these two values, a sub I comma b sub I, and a sub j comma b sub j, are the same. The a's line up and the b's line up. And here's the problem. That can't be true. Because these are all different numbers, I've got two cases to consider. One is if x sub I is smaller than x sub j, and the other one is if x sub I is bigger than x sub j. So if x sub I is smaller than x sub j, that means x sub j is at the beginning of an increasing sequence of length a sub j. That's what a sub j is measuring. So I'm starting here and I can go up a sub j times, which means I can just tack on x sub I to the beginning of that sequence. I want all my numbers to go up starting with x sub j. Well, if I'm starting with x sub I instead, I can do that same sequence, start x sub I, jump right from x sub I to x sub j, and then keep going. So x sub I is at the beginning of an increasing sequence of length a sub j plus 1. So a sub I, the longest sequence starting at x sub I that's all increasing, has to be greater than or equal to a sub j plus 1. But they're supposed to be equal. A sub I is supposed to be equal to a sub j. So this is bad. That can't happen. And the opposite happens here. If x sub I is bigger, then x sub j is supposed to be at the beginning of a decreasing sequence of length b sub j. But I can tack on x sub I to the beginning of that sequence. Add x sub I to get a longer sequence. Just add a room. So what that tells us is we can't have had it. We cannot manage to keep all of our a sub i's less than or equal to n and b sub i's less than or equal to n. Pigeonhole principle says that can't happen. One of them has to be at least n plus 1, so there has to be a subsequence that's long enough. You have to find a subsequence with n plus 1 elements. Okay, we are way overdue for our break. Let's take 3 minutes this time. We'll come back 9:28. We'll shift gears when we come back. We'll talk about something different. Go ahead, get up, stretch, grab some water, reset so we can focus for the rest of the class, because I think I lost some of you there. Might have to go back and watch that in the recording. I'm really stiff this morning. I could use a stretch. Okay, let's gather back, refocus. 17 more minutes. We'll push through. We'll get to the end of this lecture. We can do it together. Put all that pigeonhole principle stuff behind us. I want to go back to talking about functions. Since it's the end of the week, let's draw some pictures. I want to think of functions as little factories. So here's my F factory. It's got some nice smokestacks. And the way F works is it takes domain in, and it does whatever it does inside the factory, and it spits codomain out. So here F is a function from A to B. And I don't know what it does inside there. Right? Some function, maybe it's got a formula with it, maybe it's just some arrows pointing, but that's our factory. And if you pay any attention at all to the news, you've heard the term supply chain recently. So you know that once a factory takes a material and turns it into something else, yeah, maybe this gets sent to you and you're buying directly from the factory, but it's also possible that there's another factory just waiting to take that output from the first factory and turn it into input. The codomain of F is the domain of G. G takes what F produces and turns it into something else. So maybe wheat gets sent to the factory F, F turns the wheat into flour, and then G takes the flour, turns it into bread. Now, if you're a good capitalist, you want to control this whole process. If these are two different factories, then there's inefficiency. So what you really want to do is build a big factory that takes A as input, and then inside you've got one part of your factory, one corporation or whatever that takes A and turns it into B, and then all in the same family, that B gets turned into C. It's all in one big factory. And from the outside, you can't see the inner workings. All you see is A's going in and C's coming out. So we have a function here that turns A's into C's. And we need a good name for it. And our name is G composed with F. G composed with F turns A's into C's directly. It's a brand new function. It's its own function. And it's named this in deference to where it came from these F and G's. So, more formally, if F is a function from A to B, and G is a function from B to C, then G composed with F is a function from A to C defined by G composed with F. If you give me any element in A, the output is G of F of A. F will turn my A into a B, and G will take that B and turn it into a C. This lets me link up functions as long as their domain and codomain line up in this special way. Okay, so this is something hopefully you've seen before back in pre-calculus. So here's my question. Here's what I want to do. What can we say about G composed with F if we know things about F and G. So let's start with a basic example. So theorem. If F is a bijection from A to B, and G is a bijection from B to C, what do you think is the theorem? What can we say? A to C, what about A to C? Yeah, right? Then G composed with F is a bijection from A to C. Okay, and I'm not going to prove this theorem, but in order to prove it, you would show everything in B, everything in C has exactly one thing in A that it goes to. So F is an onto function, G is an onto function, so F composed with G is an onto function, and blah, blah, blah. Okay. So things like this make sense. If F is a bijection and G is a bijection, then G composed with F is a bijection. Now I want to ask the opposite question. If G composed with F is a bijection, what do we know about F and G? Do we know that F and G are both bijections? Let me draw you some pictures. If this is F, and G, is F a bijection? F is not a bijection. Why is F not a bijection? If it's not a bijection, that means it's either not one-to-one or it's not onto. Good, it's not onto. Is G a bijection? G is also not a bijection. Why is G not a bijection? It's not one-to-one. But is G composed with F a bijection? Well, let's figure out what G composed with F is. G composed with F, I'm only inputting A's. I input A into the G composed with F factory. Once it's in the factory, it's hidden from me. I don't see what happens. All I know is what comes out the other side. If I input A, it goes in here, it comes out here. That's G composed with F of A. That's G composed with F of A. Is G composed with F a bijection? Yes. So f is not a bijection because f is not onto, and g is not a bijection because g is not one-to-one, but g composed with f is still a bijection. So what this tells us is f does not have to be onto for us to have an onto function. G does not have to be one-to-one for us to have a one-to-one function. But we can still say the following. If G composed with F is one-to-one, so G composed with F is an injection, what does have to be true? If F is not one-to-one, do I have any chance that G composed with F is one-to-one? Either one of them is one-to-one or onto. In particular, if G composed with F is a one-to-one, then so is F. Right? Think about what it would mean otherwise. Here's part of A, part of B, and part of C. I've got two elements of A. F is not one-to-one, so I've got two elements of A that point to the same element of B. And then that element of B only gets to point to one thing. So when I look at the composition, G composed with F, this element gets sent here, and this element gets sent here, and G composed with F is not actually one-to-one. So it's not that either one of them is one-to-one. If G composed with F is one-to-one, then F has to be one-to-one. And so what do we think about onto? If G composed with F is onto, then what do we know? Then G has to be onto. Because I don't care what happens over here in A. If there's some element in C that nothing in B points to, that means there's no way that G composed with F is going to give me this value. I don't care where you draw the arrows between A and B. There's nothing that's going to start here and end here, because nothing goes from B to C to this element in C. So if G composed with F is onto, then G has to be onto. If G composed with F is one-to-one, then F has to be one-to-one. But, as we saw up here, the opposites are not true. Or the other is not true. If G composed with F is one-to-one, that does not mean G has to be one-to-one. And if G composed with F is onto, that does not mean F has to be onto. One last thing for today, and then we'll wrap it up, call it a day. There's no rule that says C can't be A. I can have F be a function from A to B, and G can be a function from B to A. And that means that g composed with f is a function from a back to itself. And one really interesting function from a to itself is the least interesting function, identity of a. That's a function from a to a, where identity of a, if you give me any element in a, I just spit it right back out. So this is the picture for any function, identity of a. I've got some elements in a, and I'm sending them back to a, and I just send them straight across. Nothing changes. So here's an important definition. If f is a function from a to b, and g is a function from b to a, and g composed with f is equal as a function to the identity function on a, and f composed with g, so this is a function, I start with g, I plug in a b, I get out an a, I take that a, I shove it into f, f gives me back a b. This is a function is equal to the identity on b. That's how we're going to define an inverse function. Then g is the inverse of f. Because what we're doing is we're undoing anything f does. One more picture. I've got a and b, and I can think of this as another copy of a. F is sending stuff all over the place. But g undoes anything f does, so that when I compose the two functions, everything ends up right back where it started. That's the same as saying I've undone f. That's what we mean when we talk about it. Okay, I'm out of time, so I'll stop there for today. Good luck on quiz, what are you up to, 9, 10? Something like that. I think we're up to quiz 9, so that'll be releasing soon, over this weekend. Office hours later today, from 11:30 to 12:30. Happy to talk more then. Otherwise, have a nice weekend. See everybody next week.